The James Webb Space Telescope has now produced another image that shows something is seriously wrong with our universe. Either our space is going crazy, which would mean it has some kind of intelligence, or our scientists simply got it wrong. The fact is that since the launch of the new telescope, we are experiencing a crisis in world science the likes of which we have never seen before. It seems as if the new findings are trying to tell us something urgent, but so far, scientists are arguing more than they can present us with real new facts and truths. Does this mean the end of everything? No stone has been left unturned since the JWST showed us images of galaxies that are so old and so perfect that they shouldn't even exist. This was the beginning of a drama in modern science that continues to the present day. More and more images show even crazier phenomena and impossibilities. Nothing in the young universe is the way scientists thought it would be, and now it's also clear that the entire universe is not the way our scientists thought it would be. Until now, researchers have assumed that the universe is homogeneous, meaning that its large structures are largely uniform in shape. But now, there are dozens of indications that the universe is, in fact, inhomogeneous, and this calls into question some of the basic assumptions about the nature of the cosmos. The idea of a homogeneous universe goes back to the cosmology of the early 20th century. Albert Einstein introduced the cosmological constant in his general theory of relativity, describing a static universe that neither expands nor contracts. A little later, it became clear that we do not live in a static universe, but that this space with all its phenomena is highly dynamic. There is nothing that does not move in this universe. However, the physicist Alexander Friedmann came to the conclusion that Einstein's field equations also work with an expanding or contracting universe. Georges Lemaitre then proposed the idea of the Big Bang, in which the universe expanded from a single point. These developments led to the idea of a homogeneous and isotropic universe, which is anchored in the so-called cosmological principle. The principle states that the universe is homogeneous and isotropic on large scales, meaning that it looks the same everywhere, regardless of where you look. Let's compare this to a landscape. A homogeneous and isotropic landscape would be like a vast, endless desert in which the sand is evenly distributed everywhere and in which there are no hills, valleys, or other geographical features. No matter which direction you look or where you go, the landscape looks the same everywhere, and there are no preferred or special places. In the case of the universe, this would mean that stars, galaxies, cosmic nebulae, and other phenomena are roughly evenly distributed in space. However, recent discoveries by the James Webb Space Telescope and other astronomical observations have shown that the universe may not be as homogeneous and isotropic as previously thought. The quasars and the Great Ring prove it. It may be strange to imagine the entire universe as a landscape, but on closer inspection, this idea is not so far-fetched, only the dimensions are somewhat larger. Here we have galaxies with millions or billions of stars. These wander around the universe along filaments and come together in groups. We know of gigantic empty spaces, the voids, black holes, and other phenomena. All these objects take part in the cosmic spectacle. Researchers have now discovered that one side of the sky has about 0.5% more quasars than the other side. Quasars are extremely bright galactic nuclei powered by supermassive black holes. This uneven distribution further suggests that the matter in the universe is not evenly distributed after all. This process drastically reduced the number of free electrons, making the universe transparent to photons. Photons could finally travel unhindered. Light was created, and the decoupling of matter and radiation continued. These released photons are what we see today as cosmic background radiation. It was the uniform distribution of CMB radiation that led scientists to believe that the universe was almost homogeneous and isotropic. It may have been more than 13 billion years ago when it was smaller, but now imagine, what if the universe is not expanding in an empty space, but in a space where something already is? The Big Bang and the distribution of matter shortly afterward may have been homogeneous, but then the expanding universe encountered obstacles that disrupted the homogeneity. These obstacles can be many things, but they all lead to fantastic theories that delight space fans, but give scientists a headache. The old knowledge of the Big Bang states that space only came into being with the Big Bang. The expanding universe is space. According to old theories, there is nothing outside of this space. Quantum physics has already proven that nothing cannot exist, and quantum physics has shown that a multiverse with many nested dimensions and countless universes of different shapes, sizes, and natures is more likely than the one universe in which we live. So, what if our universe expands into a space in which other universes, dimensions, and previously unknown structures exist? This would, of course, mean that it encounters obstacles, sends other universes or dimensions away during its expansion, or they exert resistance on our universe. An initially homogeneous Big Bang would then become inhomogeneous as a result of these encounters. Such considerations are exciting, but despite the many inconsistencies in astrophysics, they currently receive very little official attention. Is our own Earth the proof? You won't believe it, but some courageous researchers who support theories such as the multiverse have come up with an interesting comparison. Our Earth also began as a homogeneous world. Planets in their early stages are collections of gas and dust, just like early suns are. Then they slowly develop, become more independent, take on an individual shape, wander around within the solar system, collide with other celestial bodies, and change. In the beginning, the Earth was a glowing hot ball, and the matter was evenly distributed. Then a heterogeneous structure developed, at least on the surface. We have large oceans and land masses that are not necessarily evenly distributed across the globe, but more randomly. The Pacific is huge, just as the Eurasian continent is very large. Africa is almost directly adjacent, while the American continents are elongated and slender. We also have more heterogeneous structures within the oceans and on the continents, deep-sea crevices and trenches, shallow sections, lagoon seas, etc. Deserts, high mountains, heavily populated areas, and sparsely populated regions have formed on the land masses. But what can we learn from this inhomogeneity in relation to the universe? Well, our Earth shows very well that the planet has changed over millions of years from a homogeneous world into a heterogeneous world, at least in part. At least the rocky planets all show traces of such changes. Mars, Venus, and Mercury also have heterogeneous structures, albeit not as extreme as on Earth. If we look at the rest of the solar system, the gas giants are homogeneous planets that have probably hardly changed their appearance for millions of years. But the diversity of our planets alone again shows the uneven distribution of matter and gas within a solar system. If we come back to the landscape of our universe, it is therefore quite conceivable that a cosmos takes on heterogeneous features in the course of its evolution, and we must come to terms with the idea that our universe is an even more dynamic entity than we previously thought. The latest discoveries of the James Webb Space Telescope have shown that our science has been wrong in many ways. The old cosmology is crumbling, and we may now have to recognize that even physical forces undergo evolution and change over time. The second discovery that speaks against the theory of a homogeneous and isotropic universe are two extremely large cosmic structures, the Big Ring and the Giant Arc, formed by galaxies and galaxy clusters. These structures are so large that they exceed the scale on which the universe is supposed to be homogeneous and isotropic. Basically, they are so large that our measurement techniques fail here. Such megastructures show that there are high mountains within the landscape of the universe, and nobody currently knows how they have emerged from or fit into the overall structure. But these are just the latest discoveries that are slowly but surely reinforcing the suspicion of a heterogeneous universe. Before these latest exciting discoveries, there were already indications from the different expansion rates of the universe. Here, different methods of measuring the expansion rate of the universe gave different results. We know this difference as the Hubble tension. If the universe is not the same everywhere, this would explain why it is not expanding uniformly. Somewhere between the levels of the cosmic background radiation and the seeds, there could be a previously unknown layer of the universe or a force that is responsible for the measurement differences. Or the universe is not expanding uniformly because there is a cosmic mountain somewhere in the way. The new telescope has its part to play in current research, as scientists have used the James Webb Space Telescope to confirm the Hubble tension. Why does the cosmic background radiation show an even distribution of matter? Do you want to know a really curious fact and a fantastic theory? Let's take another look at the cosmic background radiation, or CMB for short. It does indeed show a uniform distribution of matter. The CMB is considered to be the afterglow of the Big Bang and is basically uniform microwave radiation. the radiation originated at a time around 380,000 years after the Big Bang, when the universe had cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This moment is known as recombination. Before recombination, the universe was a hot, dense plasma of ions and electrons that constantly collided with each other and scattered photons. These constant collisions ensured that the matter and radiation in the universe were tightly coupled and in thermodynamic equilibrium. During this time, radiation was strongly scattered by the dense matter, preventing it from traveling long distances without encountering particles. As the universe continued to expand and cool, temperatures eventually dropped below about 3000 Kelvin, allowing electrons to combine with protons to form neutral hydrogen.